All right, so today's topic, we're looking at chapter 4.5. We're looking at the general multiplication rule and tree diagrams. So we use this general rule when we're looking at more than one event. So if we say probability of A and B occurring, the implication is that it's going to be two events, sometimes more. So the general rule says we multiply the probability of event A to the probability of event B, given that A has already occurred. So this notation, we've seen it before. We know that we use it for conditional probabilities. It reads as B given A. So for both events to occur, the first one must occur. Okay, a reminder about conditional probability. We know that this reads as B given A, right? Probability of event B given A has already occurred. The structure of it, we're looking at probability of A and B over probability of A, both over the given. So if I check this with the formula, let me make a little note here. Okay, so here, if I want to rework it back into this structure, I can clear my fraction, so I can multiply both sides by the probability of event A. So then on the right-hand side, here, right, that's just 1 to 1. And I'm left with probability of A and B is equal to the probability of A, right here, probability of A, times the probability of B given A. So I'm being a little bit more formal than I usually am, but we do see this notation in many different stat books, and I want to make sure you're at least exposed to it. So when we're multiplying, right, two or more events, we want to always be conscious of, is it a dependent situation, right? Is it contingent on a previous event playing out first? So let me show you a few examples and then show you how we do it as a tree diagram as well. All right, so first we're looking at the Pew Internet and American Life Project found that 93% of teenagers, so ages 12 to 17, use the internet. And 55% of online teens have posted a profile on a social networking site. Find the probability that a randomly selected teen uses the internet and has posted a profile. All right, so here we're looking at probability of internet, right, uses the internet and has a social networking profile. I'll just call that profile. Okay, so first step is looking at picking a teenager who uses the internet. What is the likelihood of that playing out? Okay, and then we are looking at the probability of picking someone who has a profile, right, a social networking profile, with the assumption that to be able to have an online presence, you must use the internet. So social media profile from among those that we already know use the internet. Okay, so again, I'm just writing that out in formal notation. So here we're told that 93% of teenagers between these ages, they use the internet. So let me write that in decimal form. Okay, and then we're going to multiply that by the percent of online teens who have posted a profile on a social networking site, because that 55%, those who have a profile, right, we are assuming that they have internet access to be able to have that profile. So we multiply that by the 0.55. Okay, in decimal form, that's going to come out as 0.5115. Okay, but I'll take it as a percentage, 2 decimal spots. So we'll say 51.15%. Okay, and now we get into our tree diagrams. So here a tree diagram shows the sample space of a chance process involving multiple stages. The probability of each outcome is shown on the corresponding branch of the tree. All probabilities after the first stage are conditional probabilities. That part is essential. So everything that happens after the first stage is contingent on what happened prior. Okay, so here is our first scenario. We'll see another one on the flip side. All right, we've got Shannon. Shannon hits the snooze button on her alarm 60% of school days. If she hits snooze, then there's a 70% probability that she makes it to her first class on time. If she doesn't hit snooze and gets up right away, there's a 90% probability that she makes it to class on time. Suppose we select a school day at random and record whether Shannon hits the snooze button and whether she arrives to class on time. Make a tree diagram to summarize the possible outcomes and calculate each probability. Okay, so step 1, stage 1. We have 2 choices. She either snoozes or she doesn't. We'll say no snooze. Okay, and then second stage, she's either on time or she's late. It has to be one of those two, on time or late. Okay, so we have the bones of the situation established. Now I need to read through the details one more time. So she hits snooze on her alarm 60% of school days. So I'm going to put a 0.6 right here. Okay, which means that when she doesn't snooze, that would be the complement of snoozing. So 1 minus 0.6 is just 0.4. Okay, if she hits snooze, so assuming that she hits snooze, there's a 70% probability that she makes it to her first class on time. So this would be 0.7, right? She's on time. And then the complement of 0.7 would be 0.3, being late. Okay, then if she doesn't hit snooze and gets up right away, there's a 90% chance that she makes it to class on time. So no snooze, on time, 0.9. Complement, 0.1. So I'm just checking that at each stage, right, these add to 1, these add to 1, these add to 1, we're good. Now we multiply across. So 0.6 times 0.7 is going to be 0.42. 0.6 times 0.3 equals 0.18. 0.4 times 0.9 is 0.36. 0.4 times 0.1 is 0.04. Okay, so these are all of the scenarios that could play out. There are 4 different pathways, and since they represent all of the possible options that could unfold, collectively, all of these probabilities, they have to add up to 1. Okay, and if I quickly eyeball it, I can see that they do. I can also see that these two together add up to 0.6, right? Those are my snooze options. And these add up to 0.4, no snooze. Okay, so now I'm asking you a series of probabilities at the bottom of the page. Let me see if I can fit it all so we can see it. That looks good. Okay, so what is the probability that she snoozes and is on time? Again, if I show you the structure of it, we're saying the probability that she snoozes, I'll write it shorthand, times the probability that she's on time given that she snoozed, right? So again, I'm just writing that shorthand. We solve for it. That was the first pathway. So snoozed and on time given that she snoozed. That was 0.42. I'm going to write that as a percentage now. So 42%. So typically if I give you a setup that's as a percent, that's how I like to see it as your answer. All right, snoozed and late. Snoozed, and since she snoozed, resulted in being late. So we're going to put that in our formal notation. I just want you to see it. So probability of snoozing times the probability that she's late given that she snoozed. Right, that was this pathway right here, the 0.18. So 18%. All right, no snooze and on time. No snooze and then on time, but given that she did not snooze. So probability, no snooze, times probability that she's on time, given that she did not snooze. So again, that pathway right here. So 0.36, 36%. Okay, no snooze and late. So that is that last pathway right here. So probability that she did not snooze times the probability that she is late given that she did not snooze. So our least likely scenario right here, the 0.04, so 4%. All right, and then where it all builds to here in the bottom, I'm saying, well, what's the probability that she's late? So she's late on these two pathways, right? She snoozed and then is late given that she snoozed. That's this pathway right here. Okay, or she didn't snooze and was late given that she did not snooze right here. So these two pathways are where she was late. So if I add those together, the 0.18 to the 0.04, that's going to be 22%. So I'll write it as 0.22 and then 22% in the end. So 22% of the time she was late. Okay, and then lastly, what's the probability that she snoozed given that she was late? So our formal notation here really reads as snooze given late. So I'm looking at snooze and late. Okay, over late. Right, given late. Okay, so then snooze and late, right, that's this pathway right here, so 0.18. Late, well, we just solved for that right up here, right? That late was really taking the 0.18 plus 0.04, so that is the 0.22. So we get about 0.8182, so 4 decimal spots for when we're looking at it in decimal form. I like it to be to the nearest 10,000th. And then as a percent, we'd say that that's about 81.82%. So we have an 81.82% chance of snoozing from among those days where she was late. All right, let's do it one more time. So flip it over. Let's go to the back. All right, example 3. So here many women choose to have annual mammograms to screen for breast cancer after age 40. A mammogram isn't foolproof. Sometimes the test suggests that a woman has breast cancer when she really doesn't. We call that a false positive, right? It falsely shows that she's positive when she's not. Other times the test says that a woman doesn't have breast cancer when she actually does. That's a false negative, right? It falsely tells her that it's negative when really she does have breast cancer. Suppose we know the following information about breast cancer and mammograms. So first, we know that 1% of women aged 40 or over in this population has breast cancer. For women who have breast cancer, the probability of a negative mammogram is 3%. For women who don't have breast cancer, the probability of a positive mammogram is 6%. Okay, we want to make that tree diagram again, summarize our possible outcomes, calculate each probability. All right, so we have first stage. Either has breast cancer or not. Okay, and then the mammogram is positive or negative. Okay, here, positive or negative. All right, so that's the bones of it. Let me slide it to here. Now we add in the information that we are given. So we're told to suppose that 1% of women aged 40 or over in this population has breast cancer. So as a decimal, that is 0.01, right? It's 1/100th, 1%. So no breast cancer would be 0.99. That is its complement. Okay, for women who have breast cancer, here, the probability of a negative mammogram is 3%, so 0.03, right? That's our false negative right here. So the positive here would be the complement, 0.97. For women who don't have breast cancer, the probability of a positive mammogram is 6%. That is the false positive, right? Showing positive when really there's no breast cancer. Okay, complement here is 0.94. Okay, multiply across each pathway. So here 0.01 times 0.97 gets us 0.0097. Okay, here 0.01 times 0.03 would be 0.0003. But let me show you what that looks like in the calculator. So 0.01 times 0.03, right? It's giving it to me in scientific notation. It's saying something that looks weird. 3e negative 4. So what that means is if you drop your 3 down, put a decimal beside it, 3.0, it's saying move that decimal 4 units to the left. So 1, 2, 3, 4. Here's your new decimal. Put in those zeros. And now it's in standard form. So 0.0003, right? There are 3 zeros in front of that 3. So that's how we just convert it. when our calculator shows it to us in scientific notation. It's like saying 3 times 10 to the negative 4th power. All right, then this next pathway, 0.99 times 0.06, 0.0594. No breast cancer, negative mammogram, 0.99 times 0.94 gets us 0.9306. So again, take a moment, make sure that you eyeball it, make sure that all of these probabilities add up to 1. They look good, so then we move forward. So now I'm asking you a series of questions that rely us. We must go back and look at this tree diagram. So they rely on the graphic. All right, so breast cancer and positive mammogram. So really it's saying breast cancer and positive mammogram given breast cancer. I won't make us write the formal notation this time. So that's that first pathway right here. So 0.0097, but I'll write that as 0.97%. Breast cancer and negative mammogram, right? So it's saying breast cancer, negative mammogram given breast cancer. So here we're looking at that second pathway, 0.0003 or 0.03%, right? That is unlikely, right? This is that false negative scenario. It's very unlikely. Okay, no breast cancer and positive mammogram. So this is that false positive. That's this pathway right here, 0.0594, 5.94%. Okay, no breast cancer and negative mammogram, right? That last pathway right here, 0.9306, 93.06%. All right, and then I'm saying, how about just a positive mammogram? So we could be an individual, right, that has breast cancer and gets a positive mammogram. So right here. Or no breast cancer, still positive mammogram right here. So I want to add those up. 0.0097 plus 0.0594. 0.0691. So about 6.91%. Okay, and then lastly, breast cancer given positive mammogram. So here we're looking at breast cancer and positive mammogram from among all of those positive mammograms. All right, so if I'm looking at my probabilities, I'm looking at breast cancer and positive. So I'm pulling this figure right here, 0.0097. I'm going to divide that by my total positive mammograms, right? I just solved for that right here. So 0.0691, right? Again, it's from adding those two pathways that resulted in a positive mammogram. And it's going to give me about 0.1404 or 14.04%. But again, it's important to me that you understand the context of that. What does that actually mean? Right? It's saying that among women who have a positive mammogram, right, 14.04% actually have breast cancer, right? So let me write that down. So among women who have a positive mammogram, 14.04% have breast cancer. Okay. All right, I got two more and we're done. All right, so here we go. Example 4. So in a stat class, we have 30 students. The gender breakdown is 10 male, 20 female. If we pick 2 students at random, what is the probability that... All right, so here I'm saying both are female. So what we have to think here is, how are my events affected by what happened first? So I have to think, okay, first pick is a female. How many females do we have? We have 20. So first pick is a 20 out of 30 probability, right? So first pick is picking a female. Sometimes I write that. So I'll put a little F here right there for female. Second pick also female. Okay, so first pick is a female. And then multiply. So, and then event 2, we pick another female. But the issue is that we're not going to pick the same one. So we now have one less female and one less student overall. Now, when I type this in, I'm a fan of parentheses. So when I type this in, I'm going to use parentheses and say 20 divided by 30 times 19 divided by 29. I hit enter. I do math frac. It's beautiful. Reduces my fraction down. So I'll say 38 out of 87. So I'm thinking of, what is event 1? How do I define that? And then how is event 2? Sometimes there will be 3. How does it rely on what happened first? What changes in my numerator? What changes in my denominator? Because this is clearly a dependent situation. My second event is contingent on what happened first. All right, scenario B. The first is male and the second is female. So first pick is a male. I have 10 males out of 30 students. And then my next pick is female. Well, I still have 20 females because my first pick was a male. So my numerator here is 20, but I have one less student to choose from. So my denominator is now one less, 29. So again, when I multiply that out, I'm going to say 10 divided by 30 times 20 divided by 29. Like that. Enter. Math frac. So 20 out of 87 is the chance of this playing out. All right, last one. Back to cards. So it helps to see your deck of cards that I gave you. Might help to pull that out to visualize. You might know it by now. All right, so find the probability of drawing the following 3 consecutive cards, so 3 in a row, from a standard deck without replacement. So without replacement, that means that I'm not putting the card back into the deck, right? So that creates another dependent situation because my probabilities will change as I work through the sequence of events. Let me show you how. So here I'm saying, how about 3 hearts in a row? So I have a heart, and a heart. So first pick is a heart. I have 13 hearts out of 52 cards. But I'm not putting that card back into the deck. So when I draw another card, now I have one less heart, so 12, and one less card, 51. So this second draw is contingent on what happened first. And now we pick another heart. So one less heart, one less card. So now 11 over 50. So again, I type that into my calculator. I do my math frac. I get 11 over 850. All right, then I'm saying, how about face card, and then an ace. So first pick is a face card. I have 12 face cards out of 52 cards. But again, I'm not putting that card back into the deck, and I draw a second card, also a face card. I have one less face card. I have one less card total. So now 11 out of 51. I don't put that card back into the deck, and now I draw my last card. It's an ace. Well, I still have all 4 aces, but I have one less card. So 4 out of 50. I type that into my calculator. I math frac it. It gives me 22 out of 5,525. All right, I hope this last layer makes sense. I hope you guys are doing well. Have a good rest of your day.